A meter, the boiling point rises by 3 degrees Celsius. Water 10 meters deep has a boiling point of 120 degrees Celsius. Let's take a closer look at Pahutu geyser erupting. We took some thermographic images of the hot water spurting out. Now the water can be superheated to 103 degrees Celsius. Now that's the white area. Hotter than 100 degrees Celsius, but not yet boiling, it surges from the ground. We can assume that deep underground, the water is heated to even higher temperatures.
I often use a pressure cooker when cooking in order to shorten cooking times. It's very convenient. A pressure cooker allows the water to reach a higher temperature.
So you're familiar with the concept?
Yes, I am. It shows you the power of water. Just boiling it can produce a spectacle like a geyser.
When water is vaporized into steam, a huge amount of pressure is generated. At the time of the Industrial Revolution, we learned how to use this in steam engines. In fact, harnessing steam power was one of the things that made the Industrial Revolution possible.
A New Zealand geyser has shown us the power of superheated water. For our next spectacle, we travel to Zao in northeastern Japan.
The Zao mountain range runs through Miyagi and Yamagata prefectures. During the winter, its trees become cloaked in pure white. This is soft rime ice. It may look like ordinary snow, but it's not. In the entire world, it is only here in Zao and at a few other spots in Japan that so many soft rime trees like this can be seen. How does the soft rime ice form? November, before the soft rime ice forms on the forest. The mountain slopes are forested with a species of tree called Mary's fir. Branches dense with small needles provide a platform for the soft rime. In January, soft rime forms quickly. The forest is transformed as the green trees are swallowed up by white ice. A close look at the surface of the soft rime reveals a remarkable pattern. This pattern covers the entire surface of the soft rime. Locals call it the shrimp tail effect. How does this pattern form? We spent a night filming the branches to find out. It was minus 13 degrees Celsius and the wind was blowing at 10 meters per second. Even though no snow is falling, an amazing phenomenon occurs. Suddenly, white ice begins building up on the surface of the needles. As it grows, the shrimp tail pattern appears. The wind is blowing from the right side of the screen. The white buildup grows on the upwind side, so what is happening on the tips of the needles? It's time to get the microscope. A Mary's fir needle is set under it. We zoom in on the tip. The entire setup is brought outdoors in an effort to capture under a microscope the moments when soft rime forms. The crew endure roaring winds for 30 minutes.
It's unbelievably cold.
The shrimp tail effect is even appearing on the crew. What do we see through the microscope? Even when no snow is falling, tiny crystals of ice 1/50th of a millimeter in size form on the tip of the needle. Analysis shows that tiny water droplets fly in from the right side of the screen and turn to ice when they touch the needle.
The shrimp tail effect is caused by a stream of flying water droplets that freeze instantaneously, one after another, over and over again. On the upwind side, the ice continues to accumulate. A huge amount of soft rime forms.
But the droplets that form soft rime ice are no ordinary water. Here is a plastic bottle full of the same kind of water as the droplets.
Why does it freeze instantaneously?
Yes, Suzanne, would you measure the temperature of this unusual water?
With this,
Yes, use this thermometer. Well, it's negative, below 0 Celsius.
lower than the freezing point.
Minus 1.6 degrees Celsius.
Shouldn't it be ice at that temperature?
Yes, why hasn't it frozen?
Water that is liquid below the freezing point is called supercooled water. Water can exist as a liquid below its freezing point, but it's in a very unstable condition. Now, any kind of impact or disturbance will cause it to freeze and become stable. This is often seen in nature with cloud droplets in the upper atmosphere, supercooled below water's freezing point.
Oh, really?
In aerospace engineering, this is treated as a danger to aviation.
Research has begun that looks at the problem. The goal is to understand how to counteract the icing that occurs on aircraft due to supercooling. Aircraft fly high up where temperatures are low. The clouds and water vapor contain supercooled water that instantly freezes into ice when it comes in contact with the wings. A tragic example of what can happen occurred in 2009 during the cold of winter. In that case, a passenger aircraft went down in Buffalo, New York. The general consensus is that it was ice on the wings that reduced the aircraft's lift and led to the accident. So supercooling is a very important issue.
Clearly it is.
A phenomenon that is very beautiful, but at the same time potentially dangerous.
Supercooled water has other unusual properties. Look at this. We shot thermographic footage at night in Zao. The upwind side of the soft rime looks yellow. Now, that's the part of the tree that exhibits the shrimp tail effect. It's generating heat.
Wow, you'd expect the upwind side to be colder.
Next, we used an infrared camera to capture the freezing of supercooled water in the lab. Before it freezes, it is green, indicating a temperature of minus 3 degrees Celsius. As it begins to freeze, the color changes to red and white. The temperature rises 3 degrees. When supercooled water freezes, it releases heat. Then at 0 degrees, it turns to ice. It's a weird property of water.
Why does water generate heat when it freezes?
In liquid water, the molecules are moving vigorously and have a lot of kinetic energy. In ice, the water molecules don't move much, so the kinetic energy in ice is quite low. When water freezes, it gives up the kinetic energy. The energy given up is the so-called latent heat of freezing. So the supercooled water we saw earlier was at -3 degrees. After it released heat, the temperature rose to 0 degrees and it froze. Supercooled water is actually found everywhere in nature, throughout the world. But the degree to which soft rime ice forms is only found in Japan, in places such as Zao.
What's the secret of Zao?
Let's take a closer look at the process that's responsible.
West of the Zao Range is the Asahi Range. Supercooled water is caught up into the wind over the Asahi Range. In northeastern Japan, seasonal winds blow from the northwest during the winter. The Asahi Range and the Zao Range are directly in the path of these winds. As the seasonal winds cross the Sea of Japan, they suck up large amounts of moisture. The water vapor gradually cools until it becomes supercooled droplets. The droplets first hit the Asahi Range, but soft rime doesn't form there. The droplets are too numerous and instead fall as snow. As a result, a reduced quantity of supercooled water droplets is carried by the wind. These are transported to the Zao Range, where they form soft rime ice. This phenomenon occurs because the Zao and Asahi ranges are of roughly the same altitude. If the Asahi Range was a little taller, too many supercooled water droplets would be lost there to form soft rime. If the Asahi Range was a little lower, too many supercooled droplets would continue past it and become heavy snowfalls on the Zao Range, swamping the soft rime. It is these two parallel ranges, both around 1,800 meters in elevation, that produce the soft rime.
So water's unique properties combine with just the right geography to create those trees coated in soft rime